The format of the evening is that Martin's going to give us a talk about this month's sky night to have a little look at. So that's going to be the first thing. Following that, Jerry will introduce our guest speaker. We've got a fascinating subject about Tycho Brahe, and really looking forward to that. Following the meeting, there will be an opportunity for you to ask questions. So if you want to ask a question, rather than try and attract my attention by putting your hands up, please don't. If you could use the chat button at the bottom, then we can see your questions turning up, and Jerry can field them to our speaker. He can field them to Robin after the talk. Following that, just a few closing announcements for you all about the next meetings and so on. And we anticipate finishing somewhere around about 9:45, 10 o'clock. That's the aim. So the first thing on here is for me to try and find Martin.
Good evening, everybody. I'm just going to my presentation up for you. So let me just go here. Okay, so I hope you can all hear me okay. I'm just going to quickly go back over what some of the things we covered last month. One of the things we were talking about, I spent quite a bit of time talking about the opposition of Mars, and I felt it was worth just mentioning again this evening, as the opposition is actually last night and tonight, basically. So if you get an opportunity, if it's clear tonight, to go out and have a look at Mars, I would highly recommend that. It's as bright and as big as it's going to be for some time, because it will start to move away from us shortly. So this is a screenshot that I took in what did I take it in? In one of my applications. I forget what it's called at the moment, and this is where it is currently. So we can see here we've got Pisces. There's the Triangulum Galaxy, Triangulum Aries. There's Seven Sisters. So Mars is right there, so it's quite easy to find. It's in the southeast, and it will get quite high as the evening goes on. So just to briefly go back over what I was talking about, I did go through retrograde orbits and how they work, why the planets are moving in one direction, then all of a sudden they appear to go back, and then they continue to move forward. And it's merely an optical illusion created by the fact that we start to move faster than Mars in our orbit, and as we increase our speed, it appears to go backwards. So this is where we are currently. 13th was yesterday, 14th is here. So it's in the middle of the retrograde movement at the moment. And then by the 13th of November, it will start to move in its normal path. So that's just really worth going and have a look. As I say, it's it'll be a few years before we get this happening again. So I did show quite a few images last week of some pictures that Steve had taken of Mars, and quite spectacular. We've been quite lucky that no dust storms and so forth to give some really fantastic images. I noticed also Damien Peach has posted some fantastic pictures of the planet. So the other thing I was going to talk about this evening was meteor showers. We might have just missed the Draconids, which started last week. Again, these meteor showers are usually caused by debris left by comets. So this one last week, Draconids, was from this comet 21P that left its debris, and as the Earth goes around the sun, we pass into the debris field, and then we get these microscopic particles coming into the atmosphere and burning up, and that's all a meteorite is. So this one usually has a rate of about 10 meters per hour. But in past times, we've had more intense showers, 1933, 1946. But if I go forward to the next meteor shower, that's the Orionids in Orion. That's actually starting next week, well, on the 21st, 22nd of the peak for that. So if we get a clear night, definitely worth going and having a look. So that's the debris from Halley's Comet. So that's quite an interesting point. If you're going to go meteorite hunting, it's a bit of a waiting game. So what I normally do if I'm looking for meteorites is I've got a lounger and I put it out in the garden, a warm coat on, wrap up nice and warm, and lay in the lounger. And actually just looking with your eyes is the best thing, because if you try using a telescope or binoculars, by the time it passes by, you can't see it anyway. But another good thing you can do if you've got a camera and a tripod is just to do a series of long exposures and just see what you pick up, and you might be lucky. Okay, so another interesting object I did briefly discuss, I think last week, was Andromeda. I felt it was worth talking about again because it is an object that you don't necessarily need a telescope for, and especially if you're in a dark skies area. And you can also, again, using just a camera and a tripod, do a long exposure, and you'll find something like this picture here, where it just appears as a fuzzy blob. So we can just see there Andromeda, and that's just taken in someone's garden with the camera using a reasonably long exposure. Not too long, because otherwise you'll get star trails. But 30 seconds, something like that, is pretty good, unless you're tracking, of course. If you've got a tracking mount, then you can use a longer exposure. But 30 seconds to a minute will show, you'll start to show trails. These stars will appear as lines. So, and so if I go to the next, I'll just show you a picture of Andromeda I took the other day. That was taken through a telescope this week when I was waiting for another object to come up. But it's quite a large object in the sky. It occupies a lot of space. So that's quite a wide field shot I've taken there. If I used a high magnification, you'd only see a section of it. But just to try and give you a clue where to look for this, I've put two galaxies to search for at the moment. Now this one we can definitely see with the naked eye, especially if you go outside and give your eyes the time to accumulate to the dark, at least 15-20 minutes. And if you find the square of Pegasus, follow it down, 2 stars, these 2 stars to the third star, and then come up with another little star here, and then slightly off to the right of this star, and slightly above it, is M31, which is the Andromeda Galaxy. And if they're coming the other way, if you come from Cassiope as a double check, if you this V of this second part of the W of Cassiope, if you follow that line down, it'll bring you here. Now, it just appears when you're looking. Sometimes you can't. You're looking and you're looking, you can't see it, and it just appears. But if you're persistent, it's quite a novelty to find it. Now, if you come down from M31. And then follow it almost directly down, so these 2 stars here, and then down to here is M33, which is a triangulum galaxy. Now this you'd be very lucky to see this with the naked eye, but you can certainly see it with binoculars. So if you've got a good set of binoculars, again, it's certainly something to look for, especially if you know where you're looking. So a little bit of information there about finding it. So there is some information about finding Andromeda initially, finding the square Andromeda as I just described, putting 2 stars to the left, then turning 90 degrees up right, and then so with a pair of binoculars it's easier to find. But it's quite interesting to note that the photons that are falling on your eyes from Andromeda have been traveling for over 2 million years to get to your eyes. So you're actually looking back in the past there. You can also say, I also spoke about M31, which is a triangulum galaxy, and I showed you there. Again, I'd recommend, say, a pair of binoculars. I've got 10 by 50s. I can see it quite clearly with those. Once you know where to look, you can almost certainly find it quite easily. First time you find it. Okay, so there's a nice picture of the triangular galaxy that one of our photographic chap Steve took last year when we were in Spain. Spectacular picture. Won a prize for this, if I remember rightly. Astronomy now. So very pretty galaxy, I think. Picked up these areas of hydrogen in the spiral arms of the galaxy. Yeah, very impressive picture, Steve. Well done. So then we'll move on. Another interesting thing you might want to look for is this star Algol. It's actually a twin star. It's two stars together, actually. So if you've again come from Cassiope, so we were looking at Andromeda, which was down here. There's Andromeda there. But we're going to go to the other side of Cassiope, to the N star. Follow this down, past this double cluster. We've got three stars going here, and then into Perseus, and then if we come across, this is still a fairly bright star, Algol. A little bit of a description about it, sometimes called the Devil's Star, because it's quite a strong variable, and the reasons, or the Demon Star, sorry, not the Devil's Star, and the reasons for the variability is the fact here we've got two stars, and you've got a very bright central star and a not so bright star orbiting it like this. So every 2.9 days, this star blocks off the light from the bright star. So you get this drop in luminosity. So this shows a chart here. So it goes, that's the drop from when it covers from 0 to plus 1.2 there. So that's when the star's actually covering it. So that's what creates the variability on that star. So it's quite interesting. It's something that's a short period of time, and if you've got a couple of clear nights, you can actually see the difference in brightness, and that is the reason for it. So the drop in magnitude is from 2.86. So a magnitude is 2.2, but every 2.86 days, magnitude drops to 3.4. So that's another one to look for. So now we're moving into winter, so I'll just draw your attention to some of the main stars that we use for identifying objects when we're trying to look in the night sky. Certainly some interesting objects about in this section here. This is called the winter hexagon, or it's also known as the winter circle. And there's some pretty prominent stars that form that. So we've got Capella, which is bright, a very bright star here. And dropping down to the twins of Gemini, Castor and Pollux, then down to Procyon, then down to Sirius, which is the brightest star apart from the sun in our night sky, and then on from there to Rigel, which is in the Orion Nebula, the Orion constellation. The bottom corner here, there's Orion's belt, and the dagger there. And then up to Aldebaran, which is in Taurus. So this is the area of interest, and there's lots of interesting stars here. Objects to look at here. Betelgeuse is a star that's been in the news quite a bit recently because everyone's expecting it to go supernova, and it didn't. It was just a bit of fluctuation in the star's brightness. And then the famous Orion Nebula is in the belt. Well, it's not in the belt, it's in the dagger here, this section. That's where the Orion Nebula is there. That's something, again, with a pair of binoculars you can make out. So also the Milky Way runs through this section here as well. So there's a lot of activity. We'll move on to the next one. So this is something which is a very popular thing to look at in the sky. And that's the Seven Sisters, or the Pleiades. This is an image again Steve took for us when we were in Spain last year. They're quite easy to spot because they sit almost like a little mini plough in the sky, very tiny, but very bright stars. And you see them in Taurus. But if you see them magnified like this, you can see this lovely blue nebulosity around them. They're not actually around the stars themselves. It's actually sitting in front of the stars, and the stars are young, bright stars that have just been born. This is a stellar nursery here, and they're shining through the nebulosity and then highlighting it. So quite beautiful. And that's it. So I hope that was of interest to everybody. If you've got any questions, I'll be happy to answer them.
Okay, thank you very much indeed there, Martin. I always like the night sky in the winter. I think it's a little bit easier to find than the summer sky because it comes out earlier. Fascinating stuff there. Has anyone got any questions there for Martin?
Yeah, well, someone's asked me about my slides being on the but they'll be on the YouTube video. But I can, if anybody wishes to have a look at any of my presentations, I'm happy to send them a copy.
Okay, well, thank you very much indeed, Martin. We look forward to next month's talk as well. I'm now going to pass you over to Jerry, who's going to introduce tonight's speaker, which I'm sure you're going to enjoy very much. So over to you, Jerry.
Very much, Alan, and it really is a pleasure to introduce Robin Scagell. Many of you will know him from long time association with astronomy. He is a lifelong astronomer himself, vice president of the Society for Popular Astronomy, and used to run Galaxy Quest. Oh, no, sorry, Galaxy Picture Library. I'm sure you won't mind that reference. And his topic this evening is Tycho Brahe. Although he may pronounce it slightly differently, we will see. But Tycho, who some of you will know of as the name of a brilliant crater on the moon, it's appropriate because he was a brilliant astronomer, and he produced what must be the most painstakingly, fantastically accurate observations of the night sky prior to the invention of the telescope. And the consequences of that, well, you'll hear some of that in Robin's talk. So I'll say no more and let Alan pass over to Robin, who's going to tell us all about this character, and I use that word advisedly, and his most prominent feature. Over to you, Robin.
Hi, thank you very much indeed, Jerry, and thanks, Alan. And I will start by sharing my screen, and let's hope that it works this time, which it doesn't always. I need the PowerPoint slideshow with computer sound on. There we go. Can you see the title of the show there?
Yes, that's coming through.
Good. Okay. Right. Well, let's hope that it starts to run, which it's not yet. There we go. Right. Okay. Let me just pause that for a minute. Oh, going back again. I'll give you a bit of preamble to this talk. Now, one of the things I do is in normal times is to give talks aboard cruise ships. And there was one that was offered by Cunard. They put the notes around, they had a cruise going to the Baltic aboard the Queen Elizabeth. And this was last year, in August last year. And we always wanted to go to the Baltic. So I put my name down for it. And I also said, if you give me this talk, I will prepare a particular talk about the local man. That's why it's called a local hero, Tycho Brahe, because one of the places we were going to was Copenhagen, and that features in the talk we're talking about, or Denmark does. And also we went past the island, which you can see in the background there, of Ven. And so maybe as a result of my efforts to gain the gig, I got it. So that's why this is called Local Hero. But having said that, there's a lot to say about Tycho anyway, and I'm hoping that you will know a bit about Tycho already. but maybe I can give you a bit more information about him and explain why he is really such an important person. Now, the thing about Tycho is that everybody's heard about Copernicus and they've heard about Newton and maybe Kepler, but Tycho is not a name that everybody has heard of. And yet he's just as important, really, as any of those other people. The background to his work, as Jerry has said, is that he was a very detailed observer of the sky, and the information that he gave us, for example, this object here bears his name, and eventually his work led to these guys being able to land on the moon. It's a continuous sequence of knowledge which led from Tycho's observations of the sky to the moon landings, as I hope to be able to show you during the course of this talk. Okay, here's Tycho as many people have seen him. And that's his name there in, first of all, we call him Tycho Brahe. The Danes would call him Tycho Brahe, but everyone in this country calls him Tycho, so I'm going to stick with that name. Not all Danes say the name the same way. It's not, I don't think it's a common name in Denmark, but I have heard Danish people say it in different ways. But you can see his signature there. The word Tycho was a Latinization of his Danish name, which is Tiger there. I wonder if his mum called out the door, Tigger, Tigger, to get him in for a meal. But that was his name, Tycho Brahe. And in those days, if you were a man of science or a man of letters, you would Latinize your name, and that's why he became known as Tycho, or Tycho, as the Danes say. In much the same way that a lot of, I don't even notice, a lot of Chinese people now have English names as well as their Chinese ones for business purposes, and it's a question of whatever is the lingua franca at the time. Now, Tycho was born on the 14th of December, 1546, a date which I have no trouble remembering because I was born on the same date, 400 years later, of course, in 1946. In case to save you working out, that makes me 73. Now, thank you very much, Jerry, applauding madly. So I have no difficulty in remembering that date, but there are some other circumstances which I'll come on to where our lives over time sort of crossed. Now, he was actually born in Scania, not exactly where the lorries come from these days, but it's spelt the same way. But in those days, Scania or Skåne was actually part of Denmark, and you can see this is Skåne here, Scania. He was born in a castle just about there. And note that this is a picture of Denmark in Tycho's day, and note that the whole area here is all Denmark. Now nowadays this is Sweden here. We regard it as a separate country, and I won't go into the background between Sweden and Denmark, but there's a lot in between them. There's a lot of history there. But now Copenhagen is about here, and this was Denmark. This is now Denmark, and this is Sweden. But at that time, they were both together. Now, notice that they are very close together, and that's part of the story later on. That's Denmark in Tycho's day. This is Skåne here, or Scania, where he was born. Now, he was born to, unlike me, he was born to aristocratic family, but actually he was raised by his uncle. He moved from his parents' home to that of his uncle for reasons which we won't need to go into now, nothing particular sinister, but he was raised by his uncle. And in fact, they did some good in due course, because his uncle was very well in with the emperor, and as we'll see in a minute, he was a member of one of the richest families in Denmark, and this put him in the upper echelons. His parents actually didn't want him to become a scientist at all. They wanted him to go into law, which would have been a perfectly good profession for such a person. And so they sent him to university. He received a good education in Denmark and in Leipzig. And as you see, they wanted to become a civil servant. But as we'll see, he had other ideas. part of his education was to move to, I'm getting ahead of myself here. I mentioned that there were links between his life and mine. And when I was about 14, we went down as a family holiday to Folkestone. And on the seafront there is or was at the time this telescope, which those of you who are of a certain age, which as far as I can tell most of you are, you put sixpence in the slot and it says at night observe the moon. Well, when I went down to Folkestone in 1961, over the water, over the channel, there were two bright objects, and I looked at them through this telescope, and one of them was Jupiter and one of them was Saturn. And that's how it appeared in August 1961. Now, you will know, of course, that the two are very close together at the moment. They are looking a bit like that, very much the same part of the sky, just to the left of Sagittarius. Very close position, except at the moment, Jupiter and Saturn are the other way around. But nevertheless, this was the appearance at the time, and I was captivated by that, and that's what made me become an astronomer. And as you see, it also happens this year that Jupiter and Saturn are close together. Going back to Tycho, let me just again go ahead to what will happen this year. This is the appearance of the two planets in December, on December the 21st, when they will be lower down than they are now. But this is a remarkable event because they will be so close together that you will not be able to tell them apart with the naked eye. Actually, Jupiter is very much brighter than Saturn, and it may well hide Saturn in its glare. But the two, if you look closely, will be, that's at 5 p.m., which is just about the closest approach of the two, maybe a couple of hours later. But from our point of view, if we can get a clear night on the 21st of December, that will be a spectacular view through a telescope. And this is how they will appear, very close together indeed. The separation actually only 6 minutes and 6 seconds apart, which is the closest they have been since the time of Galileo. I looked back and I wondered why I couldn't remember having seen the two planets, Jupiter and Saturn, so close together before that they were in the same field of view. It does happen about every 20 years. As you know, Jupiter goes around the sun in 12 years, Saturn 29, so Jupiter's got a bit of extra work to do to catch up Saturn in the sky. And so they actually appear together every 20 years. And I thought, well, I've been observing the sky since about 1960. Why didn't I see this before? So I looked back at the various conjunctions of the two that have been taking place. There was one in 28th of May 2000, but it took place too close to the sun to be seen from the UK. You might have just seen it from other parts of the world, maybe down in Australia, but that's why we missed it. And the separation there, you can see the two was 1 degree and 10 minutes apart. So certainly not so close that you would mistake that they would merge together in the sky as seen with the naked eye. You would see them as two objects about 1 degree apart, which is about twice the moon's diameter. So not all that close. Going back to 1980, they were in the early morning sky, and again they were just over 1 degree apart. So you would have got them in, but they were in the early morning sky, and it wasn't of great interest to me. I didn't wake up early in the morning to see them. Going back another 20 years, well, 1961, this was before I got really interested in astronomy, and the separation was 14 arc minutes, so they would have been close together, but they would have been very low in the early morning sky before sunrise, so I don't think many people bothered. Going back earlier than that, before my time, in 1941, if anyone cared, the separation was 1 degree and 18 minutes, and they were in the evening sky, but again, not all that close together when you see the separation that they will be this year. And in 21, they were too close to the sun, just over 1 degree, under 1 degree, and 1901, about half a degree in the evening sky. But as you can see, these conjunctions of Jupiter and Saturn taking place about every 20 years, it's very rare for them to be so close together that they almost merge into one planet, which they will this year. So we're really looking forward to being able to see the two planets in the same field of view. Now, I think we can go back to Tycho, and this is how he would have seen the conjunction in August 1563, just under 400 years before I saw it in 1961. Now, the closest they would appear on that occasion was actually 6 minutes and 45 seconds, so almost as close as we will get this year. Tycho then was age 16, and he was looking forward to this event because it was one of the spectacles of the sky in the day before telescopes. You watch the planets moving and you wonder what they were, and this was something that he was really looking forward to. But there was a problem, because the tables that he found were 2 days in error. Now, those tables had been produced using the Copernican system. They were using the latest data, and they'd only been produced 12 years beforehand, and already they were 2 days in error. The older Alphonsine tables, which had been used since antiquity to try and predict the positions of the planets, were by then a whole month in error. And so clearly there was something going very wrong with our understanding of the motion of the planets. And this is what interested Tycho. As someone who was interested in mathematics and in the sky, this was really of great interest to him, and he resolved to find out what was going on. He decided that better observations were needed and better calculations, and this spurred him on to become a mathematician and to try and resolve this problem of the positions of the planets in the sky. How did you do that in those days? Remember that the telescope hadn't been invented at this point. It wouldn't be invented for another 40 years. All the measurements had to be made just by looking at the sky. And if you or I tried to measure the position of a planet in the sky, we would have great difficulty doing it. So how did he do it? This is roughly the way in which it was done in those days. If you were a navigator at sea, you would use this device called a cross staff, and you can see how it works, roughly speaking. You have a stick which is marked in degrees, and you have a cross across it, which you can move up and down the stick, and you align it so that the bottom half of the stick, labeled B, is on the horizon, and the top half is on the star you want to observe, and then you can measure the angle, which you can read off by the scale along the long stick there. It's a very crude sort of instrument, and of course, if you're only interested in measurements to the nearest couple of degrees or something like that, it's not too bad. But imagine trying to use that on board a ship. It's no wonder that navigation was very much a black art at in those times. But if you were on dry land and you used it very carefully, you could measure the angle between pairs of stars. But you can see there's lots of errors that can happen if you're trying to do that. Tycho tried to use such a device, and he had to do this in secret. I said his parents wanted him to become a civil servant. He was at that stage in the university town of Rostock in Germany, and he was actually able to observe through a skylight. His quarters were in the top floor of a building, and he was actually able to observe while his guardian was asleep below. So he made his observations very surreptitiously. This is Rostock around the time when he was pretty 16, and he would have been at university there. He actually entered the university at the age of 15, a very precocious young chap. That's Rostock back in the in the 16th century. Notice this church here, which I'll come on to in a minute. Nothing particularly special about it from Tycho's point of view. I'm sure he saw it. But the cruise I was on actually visited Rostock, and there you can see the same church now. A lot of it obviously is a new town now. It must have been flattened during the war. But this is Rostock today, or rather back in last August, and it was part of East Germany. The only time I've been to East Germany, it's quite interesting. Things are not as advanced as they are in West Germany, although it is a nice town, very well worth visiting. They've got a good astronomical clock in the cathedral, just those two separate buildings there. The other cathedral there has got an astronomical clock. So Tycho, when he was at Rostock, here he is. This was the time that where he engaged in perhaps what most people have heard happened to Tycho. He got into a duel with a fellow student. Now, it wasn't over a girl, as a lot of duels take place these in later times, and he came off worse, as you probably know, because he, in this duel, which was over with a fellow student over who was a better mathematician rather than anything else. And Tycho lost the bridge of his nose in the event, and you can see on that picture there that there's something funny about the top of his nose. Now, the books I read said that he was given a gold nose as a result, and Tycho is buried in Prague, and his body has been exhumed a couple of times, once at the beginning of the 20th century and again in 2010. I don't know the circumstances surrounding this and exactly why they decided to exhume his body, but it turned out that the prosthesis on his nose was actually made of brass. Now, the question is, was this because his nose, artificial nose, was actually made of brass, or was this a sneaky swap made by the undertaker at the time, who thought, well, no point in burying a perfectly good gold nose, let's swap it for one of brass, no one will notice the difference. Well, we did, but I don't know the answer to that one, but apparently it was a brass nose and not a gold one. So that's Tycho with his famous gold nose or brass nose. Now, in 1570, he returned to Scania, and although he was not fighting over a girl, he actually did get his girl. He married a local girl called Kirsten, but she was a commoner, and as a result, he was allowed to marry her, and the rules at the time in Denmark said you could do that, but she couldn't inherit his estate or his title, so the title that he had died out in that response as a result of that. And he was becoming very well known. He was quite a figure in the area, but he didn't really make his mark until November 1572, and that's when his life was transformed. What happened then? It happened in the constellation of Cassiopeia, and I guess a lot of you know what's going to come along. There was, in November 1572, a brilliant supernova in the sky in Cassiopeia, known today as Tycho's supernova, although he wasn't the one to discover it. It had been visible for a while before he spotted it, probably because of the conditions in Denmark at the time, just a cloud and all that sort of thing. But when he saw it, he recognized it straight away for what it was, a new star. Now, they didn't know it was a supernova, of course, in those days, but today we know the supernova as the explosion of a pair of stars, and there's a drawing made at the time of the pattern of Cassiopeia, not particularly well drawn, but there's the star, so that's how we know where it was at the time. And this is the remnant in the sky that we can see using radio waves in the same position as that star. Now that looks quite big there, but it's actually only about 10 arc minutes across, which is about this, well, it's smaller than Mars at the moment. It's about half the size of Mars at the moment. So it is quite a small area on the sky, and that's only visible in radio waves, and it's the remnant of the star that blew itself apart. It was a type 1A supernova, and this is how we know a supernova of this type, which is a very common type, takes place. I hope you can see the video there if I run it. Yeah, Jerry's nodding, thank you. And two stars, one orbiting the other, and what happens is that material is dumped from one star onto another as it starts to expand, and it overloads the smaller star, and that turns into that explodes, a bit like throwing fat on the fire. The extra material on the star causes it to overload and explode. That's a totally different story. That's what Tycho saw. He had no idea about what it was at the time, but this was an extraordinary event because the heavens were supposed to be fixed. He was very lucky because supernovae, as you probably know, are very rare in the Milky Way. The previous one to that was 1171. There was one before that in 1054, of course, the Crab Nebula that we know now. And the one after that, 1604, and I'll mention that later on. But since then, we haven't seen another one. And so he was very lucky. He was lucky in several ways, and seeing the supernova was one of them. Now, it caused a bit of a stir because the heavens were supposed to be unchanging. And even now, it would cause a great stir. As Martin mentioned earlier on, people were interested to hear that Betelgeuse had dimmed and were hoping, against the odds really, that it might turn into a supernova, because we haven't had one for about 400 years. But we're still waiting for that great supernova. In some galaxies, they happen quite frequently, about every 50 years or more often, but we haven't had one for quite a long time. Or if we have, we haven't seen it. It must have been hidden by dust clouds in our own galaxy. But in Tycho's day, as I say, the doctrine was that the stars were regarded as put there by God. They were immutable and couldn't be changed. And therefore, anything that changed in the sky had to be much closer to the Earth in our own atmosphere. So this was the theory that it was some kind of meteorological phenomenon, and it was a new star, and therefore it had to be close to the Earth. Tycho wanted to find out just what was going on, and so he set about measuring its position to see how it did really fit into the scheme of things. This was the view of the universe that had been laid down since Greek times, and this is what's known after the name of Ptolemy, the Earth in the middle there with the atmosphere around it, and then the moon. Well, we know the moon goes around the Earth very quickly. In terms of the motion of objects in the sky, they put Mercury next, and then Venus, and then the Sun, just looking at the rate at which they move through the heavens over a period of a year. Then Mars, Jupiter, Saturn, and then above those, the fixed stars. Now, all of these were supposed to be fixed to literally crystal spheres. Well, in those days, why not? They had to be crystal because you could see through them, but it was as good an idea as any, because the idea of the ideas that we know today just didn't occur to them. There was no evidence that of how things would be carried around the sky, if not on crystal spheres. So this was the theory that had existed from Greek times. Now, if you had crystal spheres, clearly anything that was below the moon that moved like a meteor, a shooting star in the sky, or indeed a comet, had to be below any of those spheres. So it had to be closer to the moon. And that's why if there were a change, all the fixed stars, it couldn't be a star, so it had to be closer than the moon. So Tycho started measuring its position. Now, the way he did this, bearing in mind that the only way you can measure the distance of objects that are remote from you is by parallax. We know about, as astronomers, we know about parallax in terms of measuring star distances. And in that case, you use the baseline of the diameter of the Earth's orbit around the Sun. But there's another thing called diurnal parallax, which is caused by the Earth moving, rotating. And if you look at the position of the moon in the sky at 6 p.m. and look at it again at midnight, it will have changed very slightly. Of course, this is exaggerated, but the difference is larger than you might imagine. It actually amounts to about a degree, the diurnal parallax for the moon, which is perfectly easy to measure. And what this would mean is that as you measure the position of the moon accurately in the stars, against the stars, it would move forward in little leaps, and it would slow down a bit as the Earth is moving, as your position on the Earth moves, and then it would speed up a bit as you move towards dawn. So by making careful measurements of the distance between the moon and a star, you can actually measure this, and the accuracy with which you can do it with the naked eye is not all that bad compared with the 1 degree that I'm talking about. the eye can see an angle of a few minutes of arc. So the 60 minutes of arc in a degree. So you've got quite a lot of error to play with there. And Tycho measured the position of this supernova, and to his interest and surprise, he could not detect any diurnal parallax whatsoever. So clearly it had to be more distant than the moon. Otherwise it would show diurnal parallax. Instead of being closer to the moon, it should have shown a considerable diurnal parallax if it had been more closer than the moon. After a period, the supernova faded away, and Tycho eventually wrote up his observations. And he, as I say, the star showed no movement over several months. It wasn't just a matter of days, it was several months. He published his results within a few years. It took him a long time to reduce the observations. And it was when he published it a shattering discovery, shattering quite literally, because it shattered the idea of the crystal spheres. They just couldn't exist. If that star was more distant than the moon, and yet things were changing there. And it made his name in scientific circles. Now, I mentioned he was known to the King Frederick II, and Frederick was so impressed by Tycho's work and his high status now among the European scientific community that he was given lordship of this island in the Øresund, in the middle of the not far from between the two parts of Denmark at the time, called Ven. It's called Hoven there in that's what it was called in Tycho's day, the Danish version, and now it's Ven, V-E-N, because it's now owned by Sweden. But Tycho plays a large part in the landscape of Ven even today, and he's well known throughout the area, as you can imagine. He was given lordship of Ven, and the idea was he was also given a large sum of money, a very large sum of money, to carry out his observations. This is a Ven today, and Tycho's observatory is more or less in the middle here, just about there it was located. And there's a picture, as I went on the cruise, and this is Ven as we went past it, and in the middle there you can see Tycho's observatory called Uraniborg, the Castle of the Stars. Here's a picture of it, and you can see no expense was spared in creating this. It was a massive construction. It was several stories high. It had gardens, it had outbuildings, and it was really an enormous undertaking on a small island. There's a view of it. Regrettably, none of it is visible now. It's just a few foundations and nothing to be seen now. And I'll come on to that in a minute. He was given, as I say, virtually unlimited funds. How much? Well, it cost at least 1% of Denmark's GDP. Now that compares with the Apollo program, which took about 2%, and the figure actually varies between 2% and 4%, something like that, of the Apollo program. But Tycho's work was, he was given absolutely lavish funds. How could Denmark afford this? Well, you remember I said that gap between the two parts of Denmark was very narrow. It's only a few miles apart. And that meant that Denmark could control the movement of shipping through the Øresund and could levy tolls on any ship that passed through. Otherwise, you had to go a very long way around, which in those days, it was cheaper to pay the tolls than to spend many more days on your voyage going around Denmark, around the island on which Copenhagen is situated. So Denmark was a very rich country. He had towers, you can see in the background there, for the instruments with opening roofs, and those towers all contained separate instruments. It had accommodation and staff quarters. It had a printing press, because he knew that if he was going to publish his observations, he would need to be able to print them. And he had to have a paper mill so he could make the paper as well. And so everything was all in one area for purposes of building his scientific empire. He had extensive gardens because, well, why wouldn't you? And he also had a prison. And you may wonder why. His attitude towards the locals was not the most benevolent. And here's something he wrote about the choice of a place where he was going to have an observatory. The place should be in a high locality from where it's a free view around the whole horizon without woods or mountains or other buildings intervening. Well, you can see then is a very flat island with no major things, and he was more or less in the middle of it. It is also preferable that it is a solitary place, free from the commotion of the common herd, where it is possible to enjoy philosophical tranquility. Also, although so that the things needed are available and learned and intelligent persons can frequently be admitted, while the common herd, which is no judge of such things or does not attribute to them the value they deserve, can be excluded. Well, that shows you what Tycho was like. In fact, he was quite a disliked landlord, and there were lots of complaints from the islanders about his character and his behaviour. But I suppose if you're an astronomer and you want to get on with your observations, that may chime with quite a lot of us. We would like to be perhaps left alone when carrying out our observations, although it's very nice to be able to show your telescope off to the public. There are times when you want to be alone as well. Moving on to 1577, having built his observatory, or it was in the process of being built, and some of his instruments for measuring the positions of objects were in full swing, a great comet appears. And this is another amazing coincidence. He had the great supernova in 1572 and a great comet in 1577, and he was on hand to measure their positions. And this is really very fortunate, because had it not happened that way, had to be no supernova, no comet, then Tycho's measurements may not necessarily have been as he might not have had the prestige that he eventually enjoyed. He realized that that Uraniborg was not actually the best place to build an observatory, although it had observatories on towers. And he realized that if you're trying to measure the position of objects, having your measuring instruments on a tower is not the ideal thing. And so he built Stjerneborg, or Castle of the Stars, which was largely underground. The instruments were fixed on the ground, and I believe they actually had rotating domes for the first time. And this looks like a pretty regular observatory to us. And the Castle of the Stars, it was built underground. He had in-house instrument makers, so he could keep an eye on what they were doing, because a lot of people were needed to make the very precise instruments which he needed. And what's more, he built several similar instruments, measuring the same angles in a different sort of way in each case. And it's very much the case that Tycho was well in advance of thinking of those days, where people might just make a stab at making a measurement and not take into account all the errors. But he did. He had, as you can see in the background there, here's someone using one type of measuring device, where it's a bit like the sort of crossstaff, where you align it according to the angle between things. But he also had other devices, which we'll come on to in a minute. He paid particular attention to the way you actually sighted the objects through the circle. Now, if you ever tried to sight things tight along your telescope to try and point at the stars, incidentally, I can never understand why telescopes don't have just peep sights. It would make them so much easier to align on objects if you had a foresight and a rear sight to align them on objects, instead of trying to get the object. If you're trying to find Mars, even Mars, through the finder, you've got to point the telescope in the right direction. And Tycho knew all about that, and he realized that parallax plays a part in trying to use the foresight and the backsight as well. And I'll show you how he did it in a minute. He got accurately accurate results using nothing more than eyesight, his own and his assistant's eyesight, accurate to within a minute of arc. Now that is really the limit to which the eye can see. And if your eye tried it, we would be hard pressed to get down to a minute of arc. It's a very precise measurement. But he didn't do it just by a single observation. As I say, he used several different instruments, several different observers, and comparing and contrasting the different types of measurement so that he wasn't relying upon systematic errors from just one instrument. It was all done using different people and different types of instrument. This is a reconstruction of Stjernborg today. As I mentioned, there's nothing left on the site, and it looks very much like a regular observatory, and there's no people in that one. There they are. You can see it's very much underground. It's quite a small, it's almost like the Lego version of an observatory, if you like. And I haven't actually been to see it. As I say, the nearest I've been is it's about a mile away, but nevertheless, you can see it from the ship. Some of its gardens been reconstructed, and here we are. This is my view of it from the ship, and get a close-up of it there. The church over to the left there is now at the Tycho Museum, and I would love to go and see this one of these days and see what's in there. As you're going through the Øresund, or rather that Storebelt area, you will see these little ferries crossing between Helsingborg and Helsingør, which are the Sweden and Denmark. And if you look at the name of the ship, there it is, Tycho Brahe. Tycho has got his name on the ferries. This is one of his most famous instruments, the great mural quadrant, and this is a nice version of it. There are several different versions of it. Let's look at in more detail, because it's quite interesting to see how he made his observations from this drawing. Actually, this is the famous one, the one we've always seen, but it's actually not a true representation of the situation. I always think of this as a bit like one of those cinema posters where you've got different scenes from the movie all combined into one poster, and we've got the same sort of thing here. You didn't have separate rooms with people doing things separately. This is just showing the different aspects of what went on. This, I believe, is meant to be a dog. They weren't all that good at dogs in those days, were they? And there's Tycho himself, way out of scale. This actually had, this mural quadrant actually had a diameter of about 6 feet. So, well, maybe he is in scale, but certainly not to scale with everybody else. And now the way this was used, it was actually in an enclosed room, but the only view you had of the sky was this little sort of letterbox up in the top left here. This was the aperture through which you viewed the stars, and there was a bar across it, and there were 2 slits on the backside here that you look through to make your observation. And the idea was, this is actually parallel to the bar there. You actually looked through with the 2 slits, and you made sure that the star you wanted to observe was visible through both slits, above and below the bar which you were looking at. And you can see that there are actually 2 of these back sights that you can look through to observe different altitudes. This one would have I can't help feeling that there are more experimental details that are missed out of this, but you wouldn't see much through that one. But there's the back sight, and you'll notice that the scale here is calibrated in degrees. But what's more, there are diagonals across each of the degrees. And these are quite important because as you move the back sight along here, you can actually measure its position much more accurately against that diagonal there than across the degrees. Dividing this circle was a major task as well. You had to get it particularly accurate, and that was quite a challenge in those days for the instrument makers. They did it actually very much like you did at school with a compass. You drew your compass and you kept the radius the same, then you drew another circle and that was 60 degrees, and you would then divide that by 2. So that's how they divided the circle in those days. And then having to divide it into degrees, they could divide, you could put a diagonal across, and that would give you fractions of a degree in the measurement. There are clocks here. Clocks in those days were not particularly accurate. They were pendulum clocks, but remember that Tycho was in a good position to be able to reset them very regularly, because he had the position of the sun at midday, he had the positions of the stars, and eventually you could reset the clocks and you could get a very accurate timing just by looking at the positions of the clocks. And those were quite important. And even though clocks weren't all that accurate in those days, you could actually reset them quite quickly, quite easily, I should say, compared with the stars. So there are other instruments here in the background. There's an armillary sphere there, another device there, and this one where you tilted the whole thing. So by a combination of different kinds of instruments, and here's our little assistant down there, very small chap, with a candle to illuminate what he can see, a couple of inkwells, and he was writing down the observations of the person there, so that the actual exact instant of a star's transit across the meridian could be noted. And this was how Tycho made his observations of the sky. And he used assistants, and he used different assistants using different devices, and he would swap them over so as to avoid all the personal error and systematic error which would creep into such observations. Here's a reconstruction of the mural quadrant taken by David Arditi, who has actually visited the museum there, and you get a good idea of the scale of it there. It looks a lot larger than 6 feet across, but that's the diameter of the radius of it that I was given from Tycho's documentation, so I'm not sure exactly what is going on there, but that's a reconstruction of it. And here's another one of the instruments that Tycho had constructed and would have used. And now we move on to 1597. Tycho's benefactor Frederick II had died, and the money ran out, and his successor could not see the point of employing this chap to make observations. He was a scientific he was a scientific genius and all that sort of thing, made all these wonderful observations, but there was nothing coming out of it. Just this chap sitting on his island, getting unpopular with the peasants, and not actually producing anything, not actually generating any wealth. And so he was forced to leave Uraniborg and Denmark, and the whole place was smashed up. The instruments, the assessors looked at them and thought, well, what's the point of having these? They're more valuable as scrap metal than as anything else. And so they were melted down. But fortunately, Tycho had his observations written down. And he moved to Prague, where his new benefactor was Rudolf II, the Holy Roman Emperor. And he began a new lease of life. But he then needed an assistant. And the assistant he chose was Kepler, Johannes Kepler. There was quite a lot of argy-bargy between the two of them. They didn't get on all that well. Kepler had different ideas from Tycho, and they sort of fell out after a while. And then Tycho realized the errors of his ways and got him back in again. But Tycho was exactly the right man to be in the right place at the right time, and to use his fantastically careful observations that Tycho had made of the positions of the planets over a period of about 20 years or so. And going back to that comet, incidentally, I should have said that the comet was also measured to be more distant than the moon. It showed no diurnal parallax at all in its motion. So again, it would have had to actually move through the crystal spheres, and that was really the end of the idea of crystal spheres. But that left everybody in with a bit of a problem, just what was holding the solar system and planets and the stars together. nobody had any good idea, and everything was up to grabs. And what's more, nobody really knew at that time what the structure of the solar system was. I mentioned the Ptolemaic system with the Earth at the middle. Well, quite clearly that is the obvious system to use, because we all know that everything goes around the Earth, and the sun goes around the Earth, and so does the moon, and so do the planets. So what's wrong? The idea that Copernicus put forward that the Earth was in motion was clearly nonsense, because otherwise, well, you'd all be knocked over by the wind all the time as the Earth whizzed round the sun. And clearly it was a mad idea. And what's more, the most ludicrous thing is that the stars stayed in the same position, and Tycho had proved by the observations that the stars were indeed incredibly far away. Nobody quite understood how what the stars were they little holes in the celestial sphere or whatever. Clearly they weren't as bright as the sun. They would have to be incredibly distant to be as bright as the sun, and yet it's still visible to us as just little points of light. So there was something very wrong with the whole system. But Kepler was granted all Tycho's observations and had to try and make sense of them. Tycho had his own ideas. Incidentally, I can't help thinking that Kepler there looks very much like Pete Postlethwaite, the late actor. And I think if they wanted an actor to play Kepler, it would have been Pete Postlethwaite. My wife doesn't see the resemblance, but I do. I don't know what you think. So this is the old Ptolemaic system, and one of its problems is, as Martin was saying earlier on, this business of retrograde motion, which we notice most with Mars, that as the Earth goes around its orbit, it causes Mars to loop, as you can see there. And we're in the middle of one of these retrograde loops at the moment, and it happens every time Mars is close to the Earth. And here's a simple diagram showing you why it happens. The bottom orbit is that of the Earth and the upper one is that of Mars, and Earth is moving faster in its orbit than Mars. So what happens is that as you get close to Mars, Mars actually appears to go backwards in the sky, and then eventually it starts to move forwards again as we get farther away from it. So that is the reason for those retrograde loops, which cause such problems with the Ptolemaic system, because why would Mars, if it was attached to a crystal sphere and it went round the Earth in the circle, why would it suddenly go back on itself? This was a big problem, and that's what affected all the measurements of the positions of the planets and the predictions. This was the one solution, that the Earth was actually not at the center of the whole solar system, but offset from the center, and Mars was not on the center of its orbit, but also went round in a little epicycle, and its orbit was called the Deferent. This was a sort of fiddle which they used to try and overcome the problem. And in fact, the tables weren't too bad. It wasn't such a bad way of predicting the motions of the planets. You just added more and more epicycles until they fitted the actual motions of the planets. But it was not perfect, and even Copernicus's system didn't seem to work out very well either, because he had things going around in circles as well. And this was the Copernican system. I don't know which actor could play him. Copernicus died 3 years before Tycho was born. The Copernican system had the sun in the middle, as we're used to, Mercury, Venus, Earth, Mars, etc., etc., and then the fixed stars outside those. But clearly it was nonsense, and Tycho was determined to prove that it was nonsense. And this was his idea. Instead of the planets all going around the Earth, they went round the sun, except that the sun and carrying its planets went round the Earth. So here's the Earth, there's the moon going around, and here's the sun going around the Earth as well. But the planets, he reckoned, also went round the sun rather than round the Earth. And so actually, if you look at it, this wouldn't work, because it wouldn't allow Mars to stray very far from the sun. But nevertheless, that was actually, that would be, I suppose, Mercury, Venus. I'm not quite sure how it works on this plan. There's Mercury, There's Mercury, there's Venus. Not sure how it worked, but maybe the other planets were outside that. But it was a start. There's a comet, you can see, which he reckoned was going around the sun, which went round the Earth. And that's what he wanted to prove. And he handed over his observations to Kepler to try and prove it. It avoids the Earth moving, and it avoids the mad idea that that the Earth clearly can't be moving because the stars don't show any parallax, and no crystal spheres are needed. And Kepler was the man to prove the point. So Kepler became Tycho's assistant in 1600, and a year later Tycho dies. Now this is another famous fact about Tycho, how he died. It was rumored that he was at in fact it's true that he was at a banquet given by the emperor, and Kepler tells this story, and Tycho was apparently too polite to leave the table when to answer a call of nature, and in the end his bladder was ruptured. He didn't last long, about 10 days after this, and he died. The story apparently from the exhumations of his body is that maybe he had a bladder infection anyway, and it wasn't a burst bladder, but I don't know. If any of you are in the same position, feel free to go and leave the answer the call of nature. I don't want any deaths as a result of this talk. Anyway, within a day, Kepler was appointed imperial astronomer in his place, and he was now free to create his own plan of the solar system using Tycho's observations. But he couldn't do it straight away. Poor old Kepler had a lot of things on his plate. He was, for a start, he had no idea what held the planets in orbit around the sun. He also had lots of, well, he didn't know what shape the orbits were. Everyone said that they ought to be circular, but were they? He also was interested in optics, and he devised basically the telescopes, the refracting telescope, which we use today, the more simple version known as the Keplerian telescope, with two lenses of different focal lengths rather than the Galileo one, which used a negative lens. And he also was asked to advise the emperor on astrology, so he had lots of things to do. And these are calculations. He tried lots of different ways in which to reconcile Tycho's observations, precise observations, with the movement of the planets in the sky. Here's another figure that was important at the time. William Gilbert also died just a couple of years after Tycho, as you can see. He was a physician to Queen Elizabeth, and he was also another polymath interested in all sorts of physical things. He wrote a book called De Magnete in 1600, again just before the time we're talking about, which was widely read throughout Europe, in Latin, of course, as with the classical at the time. Incidentally, Latin is still the lingua franca in some ways of astronomy. We're talking about a lot about Mars at the moment, but all the features on Mars still have Latin names, and they're named by people at JPL and NASA, but they still use the Latin names. Like, it's not the plains of Utopia, it's Utopia Planitia, for example. So they're using the Latin names rather than using English names to describe the various feature. Cerberus Fossae, the trenches of these are Latin names. Latin has not died out from our language in terms of science. And it was written De Magnete was written in Latin. And one of the things it said was that the strength of magnetism varies inversely with the distance, which is fine. And William Gilbert suggested that the same force that attracts two magnets together held the moon in orbit around the Earth. And this actually was very important in terms of Kepler's work, because Kepler now had this idea of force acting at a distance, and no crystal spheres were needed. Force was the thing that did it, and this was the birth of the idea of gravity. Before Kepler didn't invent the idea of gravity; that was left to Newton. But this was the birth of that idea. 1604, another supernova appeared, and Kepler was able to observe this. And it's a wonderful coincidence that he was able to observe one, and so was Tycho. But this one's now known as Tycho's supernova remnant, and there it's a radio view of it. Tycho, as Kepler eventually was able to calculate, work out that the only way he can make all Tycho's observations fit was to use not circles, but ellipses, with the sun at one focus of the ellipse, nothing at all at the other focus of the ellipse, and the planet going round in an ellipse around the sun. This is a somewhat exaggerated non-ellipse, but just to show you the parameters of the ellipse, we have the major axis and the minor axis, and we have perihelion and aphelion, and the semi-major axis is the average distance of the planet of the sun, and that comes up in Kepler's laws, which he formulated over a period of some time. I hope you can see this animation. You will find that this is an American one because it's got everything in American. There's no sound with it, but I shall let it run. I hope you can see it. Yep, good. Each planet is at an orbit around the sun's ellipse. The sun's center is always located at one focus of the ellipse, and there you can see the planet going around the sun in an ellipse. That was Kepler's first law, and obviously this was not a crystal sphere. His second law, imaginary line joining a planet and the sun sweeps out equal areas of space during equal time intervals as the planet orbits. And this is what we now realize, that the planet moves slowly when it's far from the sun and much more quickly when it gets close to the sun. And this applies not just to planets, but to every other body in motion in the universe as well. And that's the crucial thing. We use Kepler's second law in every field of astronomy, astrophysics, and space exploration all the time. So he was able to express that in mathematical terms in his final calculations. Kepler's third law: squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their orbits, the semi-major axis, which I showed you there. So this was the crucial one, which actually put a mathematical framework on the orbital periods of the planets. And we've got Mercury going whizzing round in 88 days, the Earth taking 365, of course, Saturn taking 29 years, and that puts the mathematical figures on all of those things. And that, cutting a very long story short, takes, I told you this was an American thing, takes us up to Newton's law of universal gravitation, cutting up about 40 years of work. And there we have Newton's laws deriving from the work of Tycho and then Kepler, and giving us what we know today as we couldn't have space travel as we know it today if it were not for the work of Tycho and of course Kepler.
And liftoff at dawn, the dawn of Orion and a new era of American space exploration.
And this, of course, led, not with this rocket, but others, to people walking on the moon, and what's more, to other things in the universe, our understanding of the universe as a whole. Stars orbiting the Milky Way black hole still obey Kepler's laws, and I'll show you this animation. You can see they move quicker when they get close to the black hole at the center of the galaxy, and then slow down again. Kepler's laws in operation with black holes right at the center of the galaxy. And these are based on actual measurements of stars close to the black hole at the center of the galaxy. So I hope I've convinced you that Tycho's work was absolutely crucial to our understanding of the universe as it is today. And if it weren't for that wonderful coincidence of the appearance of the supernova of 1572 and then the comet of 1577, if those hadn't appeared, I wonder if Tycho would have actually managed to achieve what he did. So there he is, the man himself, and I hope that you've enjoyed the presentation. Thank you very much indeed.
Well, thank you very much indeed there, Robin. That was absolutely brilliant. If you've got any questions, could you use the chat button in the middle of the screen at the bottom there and send your questions along?
Or criticisms. I expect there are things that people spotted that I did wrong. I'll stop my share.
All right. I was just fishing around for that one. They've all gone very quiet.
Right. Well, that's all right.
You must have stunned them.
Well, yes, and the bit I don't like is when I say, "Oh, well, actually, I know more than you do." But yes, I have come across that, and it's very easy to read up on the historical personalities, and there's so much more about Tycho which I haven't been able to cover, and his life was a very interesting one, and I hope I've given you a bit of an insight into that.
I find it strange. He seems to be about the only astronomer that we refer to by his first name.
That's
Everyone
true.
else, you know,
Yes.
Galileo, Newton, and so on.
Well, Galileo as well. Galileo Galilei.
Yeah. But I mean, his parents had a problem naming him, didn't they? Gave him the same name twice. Yeah.
Yes. Yes. We don't talk about Isaac, do we? Or whatever.
Come on, then.
No, there was a much smaller world in those days, so you could become known by your first name much more easily.
Yes. Perhaps it was more of a closed circle, wasn't it? That not so many people were discussing things. Thought I heard a ping coming up there. Nope.
Okay, well, I'm happy for you to move on.
All right. Well, thank you very much indeed, Robin. That's an absolutely brilliant talk there on one of the most influential people in astronomy. Doesn't seem to get the recognition which perhaps he ought to, although it is great that there is a crater on the moon named after him. So thank you very much, and we're already getting lots of people saying great talk, and thank you very much indeed.
Thank you very much
for giving out there. Okay, we will move on then, which is basically to say thank you to everybody who came along this evening. It was really lovely to see so many people. We had 46 people taking part in our meeting. Please make a note in your diaries for November the 11th, which is our next meeting, and we've got Dr. Jane Clark coming along, who's going to be talking to you about how you can measure the orbits of planets yourself. Now, I think that's absolutely brilliant that that would follow on from what Robin has told us about this evening, that we can, it's an activity which we should be able to go out and try. So I want to see everybody going out there and measuring and trying to see if you can check up on the orbits, make sure that Kepler was correct, and you can put it to good use there. So on behalf of the Hertford Astronomy Group, thank you very much indeed to tonight's guest speaker, Robin, and thank you to Martin for your presentation about the forthcoming night sky. And of course, my thanks to everybody who came along and made this evening such a successful one. Thank you very much indeed, everybody. Have a safe journey home. Good night.